Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the class of CS103 Computer Programming for GIK Institute Faculty of Computer Science and Engineering. This is one of the last lectures for the course of computer programming, where I'll be talking about recursion. We have got a few topics left for this course, and I'll be discussing about them after this lecture, or maybe at the end of the lecture. The topics that I have in my mind are that we are going to be talking about templates, about header files, about maybe a bit more about file reading and writing, and finally something about graphics. Some of you have requested me to talk about that. Of course, graphics will not be included in your final exam. However, it will be uploaded for your reference and maybe for your projects as well. You might be wanting to use it. Having said that, I think the most important topic at the moment is recursion for you, and this is the lecture on recursion. This is chapter 15 of your book, and I'm going to basically just go through the concept of recursion using the book, and hence I'm sharing the slides with you over here, and this is the chapter 15 on recursion. And let us start about what is recursion, the concepts of recursion, what you can learn in this chapter, and then we'll see each examples, actually all the examples at the end, maybe in part 2 of the same lecture series. So let's start with what you're going to learn in this particular chapter. In this chapter, you will learn about recursive definition. What is a recursive definition? What are the properties of a recursive definition? What makes something recursive in nature? Then we'll explore the concept of base case and the general case, that are two necessary cases in a recursive definition. We'll discover what a recursive algorithm is. So what properties or what kind of solutions that are required to make an algorithm recursive in nature. Similarly, we'll be talking about recursive functions, what they are, how they work, their basic operation, etc. We'll be becoming familiar with the two particular types of recursion. One of them is the direct recursion, where you call your own self directly. However, there is another form also that is possible, which is the indirect recursion. And we'll see what those concepts are and how they work. We'll then explore how to use recursive functions to implement recursive algorithms. The recursive functions are, of course, necessary types. These are the necessary type of functions which we can use to form recursive algorithms or implement recursive algorithms. And finally, since anything that can be solved using recursion can also be solved using iteration, we'll want to learn when is recursion more useful and when is iteration more useful. And with that, I think you'll be better familiar with the concept of when to use recursion and when to use iteration versus each other, right? So, of course, not every problem that can be solved through iteration can be solved through recursion, but every problem that can be solved through recursion can be solved through iteration. And we'll see some examples maybe at the end of the lecture in the second part for this. So what is recursion? So formally, the recursion is defined as solving a problem by reducing it to smaller versions of itself. Notice two particular portions here. So one is that you are basically, if I mark it with the pen, so you are trying to reduce it to smaller versions. So this is one part. You are trying to solve a problem and your solution is always reducing it to smaller versions. And the other part that is very important here is itself. So the smaller version is the same version. The version does not change. It has just become a relatively simpler, less complex problem as compared to the original problem. However, the problem still remains the same. The nature of the problem has not changed. The working for it would still be the same. And we see through examples when we talk about factorial later that how this is happening. However, you should note that this is a very powerful way to solve certain type of problems, which would become very complicated if we use iteration to solve these problems. And you'll see what I mean in the later slides. So what is a recursive definition? A recursive definition is to define a problem in terms of a smaller version of itself. So you need, whenever you try to define a problem, there's a given problem, and you say that if you give me the solution to a smaller sub-problem, which is of the same version or same type, then I can give you the, I can define the problem in terms of, I can give you the solution of the larger problem, the problem that you're asking me to solve. And when you say a smaller problem, of course, this can go on infinitely, right? I can say that give me answer of, for example, a particular, let's say 10 factorial, and you say that, give me 9 factorial and I'll give you the answer for 10 factorial. And I can go on and on and on until it basically goes on to negative infinity. And if this goes on, then the problem is that this is what we call, this is not really a recursion, but this is something that you're going to go on for infinite times. You're going to run the loop for infinite time. And this is not really what we require. Typically, what we require is we reach a particular case, a particular point, whose answer we know. And luckily, for example, for factorial, we know that 0 factorial is equal to 1. So we know the answer for that. Once I ask you for example, 5 factorial, you can actually go down to 0 factorial. And on that point, you'll get the answer directly. 0 factorial is equal to 1. And based on that, you can calculate the values upwards again. So base case, 0 factorial is what we call the base case, right? And base case is very interesting, very important. It is a necessary thing to have in a recursive definition. If you don't have a base case, you'll have infinite recursion, which is not what is generally required. And of course, the first thing is the base case. Base case is a case for which you can find the solution directly. For example, 0 factorial, you don't need to simplify it further. It is not possible to simplify it as well. And simply we can say that 0 factorial is equal to 1. That's the answer. So since the base case is clearly defined, you can then actually say that the base case is the one that is stopping the recursion. It is not going to make a call to itself or to simplify the problem any further, but just give you the solution and move on. However, anything that is the general case, the opposite of a base case is what is called general case. General case is the one where we are trying to simplify the problem to a smaller version of itself. And ultimately, we would want, or eventually we would want that the general case is simplified enough so that it reaches the base case. And once it reaches the base case, we know we are sure that the base case solution is already known. So we can simply use that solution to get the answer for a simplified version of the problem. And once you have the answer for a simplified version of the problem, you can ultimately build it back to get the final answer for the actual problem. So like I gave an example of factorial earlier on, here's the actual example as well. You've got two equations in factorials. One is what we call the base case, which is the equation 1 over here, which you can see is 0 factorial is equal to 1. So we know, like I said, that 0 factorial is 1. So this is the base case. So our main aim would be that whatever factorial you want, for example, 9 factorial, 10 factorial, 5 factorial, or whatever, we'll want to reduce it to basically n into n minus 1 factorial, right? So this is the general equation or the general case. In the general case, we'd want to reduce this problem until finally we reach the point where this value actually becomes 0 factorial. And once this is 0 factorial and you inquire about 0 factorial, I can directly give you the answer using the base case that 0 factorial is 1. And then you can actually build it back again. So if 0 factorial is 1, then 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial, which we actually wanted to identify in our initial problem, that becomes 120. So if 5 factorial is what we were inquiring for, 5 factorial was first divided up into an elementary operation, which is a multiply over here, right? So this multiply is your elementary operation. And you asked me back, give me the answer for 4 factorial, and I can just multiply it with 5 and give you the answer for 5 factorial. And once I told you again through recursion that 4 factorial is 24, you gave me the answer for 5 factorial. Similarly, for 6 factorial, it would be 6 multiplied by 120. And so on. The cycle can continue. So this is how a recursion is defined, and this is a very simple example of factorials. And you have been traditionally, since maybe primary class, you have been doing this particular recursive definition without knowing it as the formal name recursion. You might have been doing it for a long time now. This is a very simple concept. It is just that you might not have thought of it in a similar mode. So what is a recursive algorithm? A recursive algorithm is an algorithm that finds a solution by reducing problem to smaller versions of itself. So it uses recursion to find solutions. And that is what a recursive algorithm does. And when you defined a recursive definition, it had two main properties. One was that it must have one or more base cases. It is also true for recursive algorithms to have this particular property. And the second property is that the general case or the general solution must ultimately reduce to a base case. And when it reaches the base case, recursion stops, and then that is the point where basically you get the initial solution, based on which then you can build up back to get the final solution. So a recursive algorithm must have both of these properties. However, a typical recursive algorithm usually works by using recursive functions, and recursive functions are functions that call itself either directly or indirectly, and we'll see what I mean by direct or indirect. But for a very basic start, for a base case for a first year student, for now, for this particular slide at least, a function that calls itself is a recursive function. That is what you need to know for now, although I'll show you that in indirect recursion that is not necessarily true. So what you need to do is you need to think of a recursive function as having infinitely many copies of itself. So like, it's not just one object. That object has many copies that are spread over here. One uses the second uses the third, and so on. So if you have infinitely many objects spread around in the room maybe, and you call one, the one calls the second calls the third calls the fourth, and ultimately through that whole process, ultimately you get to the solution, or the solution is returned. And each call that you do, each function call that you actually perform, each copy will have its own code, right? Although it's the same code, but that code is its own, as well as its own set of parameters and local variables. So anything that is stored in a particular function will be local to that function, and each copy has its own local variable space. Each each function call has its own set of parameters that are being passed, and each time the same code is running, but it's running for a particular function call. And after you complete a particular recursive call, the control will go back to the calling function, right? The previous call, the previous function that had called this particular function, the control will be shifted back after you complete a particular recursive call. A particular solution has been found. So for example, for the base case, once you have the solution will be passed back to the function who is calling it. And we'll see some examples in the next section of this particular lecture. And typically, the execution begins from the point immediately following the recursive call. So once you make a recursive call, the control is now passed to a function, and execution will begin for that particular function. It may or may not call itself again, but once it does call itself, that is the next iteration of recursion. But if it is a base case, it is not going to call itself again. So what is direct and indirect recursion? A concept that I talked about earlier. Direct recursion is a function which calls itself, right? So there's no third party involved. A function directly calling itself, you find the same name. The name of the function is also present in the body of the function. If that is true, then this is what we call a direct recursion, right? So for example, the function factorial function, I asked you for factorial of 5. In the body of the factorial function, you can actually say factorial 4. And since you're using the same name and passing a different parameter, its own parameter, this is what we call a direct recursion. On the other hand, of course, there's something which is called indirect recursion, or what you may say a proxy recursion. A proxy recursion is where you have a third party involved. So a function that calls another function and eventually results in the original function call. So a function that calls another function, and that other function calls another function, and so on, until there is a function that is basically calling you again. So it's like a cycle again, right? However, what you need to know is that while the direct recursion is very easy to understand and to follow, the indirect recursion is really hard to follow up and catch. So a lot of times it becomes you need to make a proper diagrams to understand which function call is calling which function, and ultimately if there is an indirect recursion involved, you need to be aware of it, and that is only possible by coming up with the right diagrams. So what is a tail recursive function? A tail recursive function is a recursive function in whose last statement executed is the recursive call. So whenever the last statement is basically calling your own self again in a particular function, that function is called tail recursive function. Of course, you might have code after that as well, but if that is not the case, and instead the last last statement is the statement in which the recursive call is made, that is, those kind of functions are defined as tail recursive functions. as I was talking about recursion earlier, I talked about a concept which we call infinite recursion. What is an infinite recursion? I told you that once you are into recursion, if you call yourself and there's no base case present, then the problem that occurs is that of infinite recursion, and this is something that you need to avoid completely. So every recursive call results in another recursive call. So like I said, 9 factorial results in 8 factorial, 8 factorial results in 7 factorial, and so on, right? So if there is no base case that is present, if you don't know the answer to the base case and that is not present, then infinite recursion will continue to execute and will basically go on forever, because we can go on till negative infinity for the factorial problem. And if you don't put a limit for positive integers or for 0 factorial or 1 factorial, you're basically going to be stuck in recursion forever. And this is what I call infinite recursion. However, the problem is that each recursive call is taking up some memory space in the in your RAM, and the RAM memory space is always limited. Since computer memory is finite and limited, each function executes until the system runs out of memory, and it ultimately results in an abnormal program termination. So you'll actually want to not have infinite recursion because of limited memory space. And of course, when you were defining algorithms, if you remember the definition of an algorithm, it states that it solves a problem in a finite amount of time. So it does not go for infinite time. Since we want to solve it in a finite amount of time, if the recursion is going on for infinitely, it also takes infinite time. And hence, an infinite recursion is not really an algorithm at all by definition. So if you go back to the base definition that I defined in maybe chapter 1 or something. So that brings me to the point that ultimately, when the memory runs out, the program is going to stop running, and it is going to stop abnormally giving out some sort of memory error instead of an answer. And that is something that is not desired. So if you have an infinite recursion case, you must always make sure that you are not there's no recursion that is going on infinitely, and you are trying to avoid that, because it will ultimately return a segmentation fault, a memory fault, or some form of heap stack issue. And you'll know more about that, maybe about heaps and stacks, etc. in data structures. But that's the kind of error that you get, that there's not enough stack space. And of course, there are those XSS parameters in C++ that you can use to assign more stack space, and we might discuss that when I'm talking about practical examples for this particular chapter. So when you're designing a recursive function, you need to make sure that it does not contain infinite recursion. And how do you do that? Well, there are some certain characteristics or steps that you can follow to avoid infinite recursion. First of all, you must always understand the problem requirements. What does the problem require us to do, right? And then the second point would be, after you understand the problem statement and requirements, you need to determine the limiting conditions. What conditions are putting limits on this, right? So we need to identify those limiting conditions. So for example, for factorial problem, we know that the problem requires that we simplify the problem somehow to 0 factorial, right? And it only works for positive integers. It cannot work for negative integers. And that then means that for any positive integer we are going to work, for negative integer we cannot work. The limiting conditions here are that it does not work for negative input and only works for non-negative inputs, 0 or positive ones. The next case here is that we need to identify the base case and provide a direct solution to each base case. So the base cases that I can identify for factorial problem are 1 factorial and 0 factorial, right? So both of them, the answer is 1. And since we know that if we get a positive integer, we'll ultimately want to reduce them to 1 factorial or 0 factorial, and finally we'll have our answer. So we'll want to identify general cases. Ultimately, the general cases that are greater than 1 or 0, those are the ones that need to be solved and brought down to the base case, make a smaller version of itself. So maybe decrement 1 and find the factorial of that, multiply it with in the general case, I'll just multiply it with the value n, or that gives me the final answer. So, and I'm sure over here that, I'm kind of reducing the problem in each step towards my base case. And I'll not miss it or skip my base case at any point in my solution. If I do that, then I've probably missed the solution, and the recursion is going to go on for infinite time, and infinite recursion is going to take place, which is something that I must avoid at all costs. So this brings us to the final topic over here, which is recursion or iteration, right? So which one is better? Should we go for iteration? Should we go for recursion? Well, here's the thing. The iterative control structure is a structure which uses a loop to repeat a set of statements. So for example, we can actually solve the factorial problem using a loop as well. So 5 multiplied by 4 multiplied by, that is the source solution, then you multiply it with 3 until basically the break condition for the for loop is going to be that until n is greater than equal to 1, I am going to multiply it with n, and once I reach 0, I'm not going to multiply it, right? So the solution in this case is also possible that I get the final value as 120 for 5 factorial. For 6 factorial, I'm going to get a 720, and it goes on. But the problem here is that this is how an iterative control structure is going to be defined. In iteration, you actually use a loop. You pass it value by value, and each problem can basically be either solved by iteration or through recursion. You must know that everything is solvable by iteration. Every recursive problem, every recursion can also be solved using iteration. It's not necessary that you use recursion. However, every iterative problem cannot be solved using recursion, because sometimes the nature of a problem may change, and hence you might want it is very much possible not to use recursion. So every problem that you see, you'll basically be trying to solve it using either iteration or recursion. Everything can be solved using iteration, but not every iteration can be solved using recursion. And so when you're choosing a particular case, recursion or iteration, you must always look at nature of the problem. Is the problem solvable by using recursion? If so, it will save you a lot of time and a lot of space as well, coding space as well. However, the problem or the issue would be the memory space available and other things available. We will probably need to assign stack space. A couple of times things can be solved using iteration directly. So for example, the factorial program, we might not be wanting to use a recursive problem and a recursive solution. A recursive solution is where you basically call yourself again and again and again. So the nature of the problem is very important, if it is recursive or not. So of course, another thing is efficiency. That is how much space you have and how much time do you have to solve a particular problem. Note that when you make a function call, it assigns some space within the stack, and when you call yourself again, a new stack is allocated to you for the same function call, and that means that with all these extra function calls that are going on, this is going to affect the efficiency of the problem. If that is not if efficiency is very, very important to you, then you must always go for an iterative solution. However, if efficiency is not the main concern, if memory space and time is not your main concern, then you'd want to go for something which you call recursive solutions. And the recursive solutions are then very ideal for you because they are easier to implement, they're easier to understand, you can easily use them. So whenever a function is called, like I said, some memory space for its formal parameters and automatic local variables is allocated, right? So a new memory space is always located for the formal parameters that are being passed to a function, and the local variables that are created, either automatic or other variables, whatever there are present, the memory is allocated to them. And whenever a function is terminating or it finishes its execution, the memory space that was allocated to the function for its formal parameters and local variables will then be deallocated. Hence, that memory will be returned back to the heap, and it can be allocated to other functions from that point onwards. However, once I talk about recursive call, so each call has its own set of parameters and automatic local variables. That was what I told you before. And this is something that you need to identify, that each recursive call will have its own set of parameters as well as local variables. So if a function is called 4 times, it will create 4 sets of local variables and parameters. However, there's one main difference. Since it has not exited, it is still in the process of running, that memory space will be continued to be allocated to the calling function, while the function recursive call that was made will get its own space. And if it goes on, this is like you assign space to A calls B calls C calls D, right? So A is still active, it has not finished. A is calling A has some space allocated in memory. It then asks, it then shifts the control to B. It has not, A has not finished, so its memory is not going to be deallocated. However, since the memory space has now shifted to B, the call has shifted to B, some space will be allocated to B to, for its set of parameters and local variables. And B is going to call C. C will have more space allocated to it. Now A and B will retain the memory space while C is running. And hence, if you think of a recursive function call, A calls A calls, let's say, A calls first copy of A calls second copy of A, and so on. So in the recursive call, since the functions A copy and B, A2 copy, A3 copy, etc. are all active, we'll notice that during recursion, we are not going to stop at all. And this basically means that in our particular scenario, the recursive call is continuing to have a lot of memory space allocation going on. And with all these memory allocations, this is an overhead that affects our efficiency in the previous step, like I said before. Number one. Number two, we need to have enough stack space, because the space that we allocate to functions is through the system stack. If the system stack has not enough space allocated, we'll very soon run out of the stack space on the for the recursive call, and that is something that we should avoid at all costs, right? We should have enough stack space to run a typical middle size or medium size problem easily. Otherwise, increase the stack space if that is the scenario, and so on. So of course, there are two things that are very important when you're talking of a function call or execution of a function, be it a recursive function or normal function. That is the memory space that gets allocated to it separately for all its parameters and local variables, as well as the computer time it takes to make a function call, save everything in memory of the previous function, and just give access to the currently running function. That is the possible overhead that comes with the recursion. And you must always know that if you have an iterative counterpart implemented, it is always going to be faster than a recursive function execution. So a recursive function will always execute more slowly than its iterative counterpart. However, today's computers are very fast, and the overhead of a recursion function is not noticeable to us. If you were in maybe 1960s or 50s, recursion would have been frowned upon very much, because if you think of it, each byte of memory was very important back in those times. Now in our times, when you have memories of 16 gigabytes or 24 gigabytes, or if you're in JIK Institute, memories of 4 gigabytes, it's still quite a lot of memory, and a few bytes or kilobytes won't be noticeable. Similarly, in terms of time as well, since every process is running in a fraction of a nanoseconds, maybe a few more fraction of a nanoseconds won't really be even noticeable. And that's why the overhead of a recurrent function may not be very noticeable in today's computers. However, it was very noticeable when the resources were very small, and it took a long time to execute a particular problem. So also at other times, I think you need to make the choice of if you want to use recursion. If a problem is very apparent to be a recursive problem, only then you should go for a recursive solution. Otherwise, it's always recommended or preferred to go for the iterative solution. Sometimes it is not even possible actually to go for recursion. In that case, the iterative solution is more obvious and easier to understand. So some of you might simply use a for loop. For I is equal to whatever n, I is greater than 0, I plus plus, and basically I is greater than equal to 0, I plus plus, and then in that you basically just do that before that int n is equal to 1, and inside you just multiply n with n minus 1 and store that in your result n, and finally return n as your solution, and this is going to be your final solution as well. So that's another way of doing factorial problem without recursion, through iteration. And the other way that you can do you can solve factorial using recursion is the way like I told you before. So there's a function which calculates your factorial, and you just call it with you just pass it a single parameter, which is the factorial that you want, and inside the function there's a base case. If input I, whatever that is equal to 0 or is equal to 1, you return 1. Otherwise, you basically simplify it. You return n is equal to n multiplied by n minus 1 factorial, so factorial of n minus 1, and so on. So it continues on. We'll see that when we see the coding examples soon. So to summarize the whole talk, what is a recursion? Recursion is a process of solving a problem by reducing it to smaller versions of itself. A recursive definition actually defines the problem in terms of smaller versions of itself. So it has one or more base cases followed by a general case, which simply reduces the problem into smaller versions. The base case simply gives you the direct solution. As you remember, it does not simplify the problem any further. On the other hand, a recursive algorithm is an algorithm that solves a problem by reducing it to smaller versions of itself, and it can again only be applied on recursive problems and not on iterative problems. So a recursive algorithm has one or more base cases. Again, this is the main thing, and the general case must simplify the problem ultimately to one or the other base case ultimately. The solution to the problem in the base case is obtained directly. It is the obvious solution. It is a direct solution for a base case. However, for a general case, you need to simplify it. The general solution will break the problem into smaller versions of itself, and then it's going to give the solution. Recursive functions are functions that usually call themselves. So a factorial function will call a factorial function again. This is what we call recursion with a slightly different value. Again, a recursive function must have one or more base cases so that the infinite recursion does not happen and is kind of not is avoided throughout. Recursive algorithms are implemented using a recursive function. So that is a typical way our recursive algorithm is going to be implemented by using functions, and inside functions you're going to have recursive function calls, either direct recursive function calls or indirect recursive function calls. And I think that's all about chapter 15 here. So in this chapter we saw what recursion is, how it works, under what cases does iteration work, under what cases does recursion work, and now we'll go off to examples of chapter 15 and see how these are solved. So I hope you've learned something about recursion over here. In the next chapter, when we start on the chapter, I think I'll go for headers and templates, template classes, headers and header files, and the CPP files. Another topic that I really want to cover is file opening, file reading, appending in a file, etc. So all those three main components. Although I've discussed them when I was discussing chapter 3, input and output, in a very brief manner. However, now we can go in a bit more detail on those topics. So that's the second topic on my radar that I want to focus more on, other than templates and header files. And finally, we might go for exception handling a bit. I don't know if that is within scope here, but we might go for that, exception handling, as well as finally, the final topic would be on graphics. So you've got, according to my notebook, you actually have got 4 more topics that I am interested to cover in. All the other topics other than the graphics will be included in your final exam. However, I think the main focus would be on the basics here, the recursion, the function, the pointers, the arrays, the input output, the data types, the enum operators, and those kind of main topics. The template files, header files, exception handling, and maybe even yeah, so those topics would be important. They may also appear, but I think it would just be a basic introduction to them instead of a very detailed one, since this is your first programming course. So it might be that for headers and for templates and for the other topics that are remaining, I won't go into too much of a detail. Exception handling, etc. Right? So with that, I think I'm done with this lecture on chapter 15, recursion, and you can now go to the second part where the codes for recursion are uploaded, and you'll see how each code has basically what does each code actually discuss, and how recursion works, and how direct and indirect recursion, all of them, how do they work really. and you'll be amazed at how simple the concept is. It is just that if you see the codes directly, you might not be able to understand what's going on. Why is it recursion? But once you have the concepts learned in this lecture, then you can easily apply them over to the coding and examples. So with that, we come to an end of this lecture, and I hope to see you in the coding and example part soon. Take care. Allah Hafiz.